In this video, we will talk about capacitor and capacitance. We will explain what a capacitor is and what is capacitance. We shall also see how capacitance of a capacitor depends on the shape of that particular capacitor. We will finally do a problem and exercise to highlight these concepts. Let's begin with capacitor. A capacitor is an arrangement with two plates where charges can be stored on these two plates. And these two plates are usually separated by a very small distance, say in the range of millimeters. The two plates in a capacitor usually contains opposite charges. On one plate, there will be positive charges, and on the other plate, there will be negative charges. Examples of a capacitor are the following. You may have such a capacitor with two parallel plates. So the plate on the left may contain a positive charge, and the plate on the right have equal amount of negative charge on it. And these two plates are separated by a very small distance d, and these two plates have some surface area a meter squared. Such an arrangement is known as a parallel plate capacitor. There can also be a spherical capacitor. So you have two concentric spheres like that. Say the inner sphere would contain positive charges on it, and the outer sphere would contain negative charges on it. And these spheres will have their own radius, Ri for the inner sphere and Ro for the outer sphere. We call this a spherical capacitor. The third example is what we call the cylindrical capacitor, which consists of two very long concentric cylinders. The inner one may have its own radius, let's say Ri, and the outer cylinder with radius R0. And you can place, say, a positive charge on the surface of the inner cylinder and a negative charge on the surface of the outer cylinder. The main function of a capacitor is to store charge, and therefore energy that can be used when needed. Let's use the parallel plate capacitor arrangement to explain this fact. So in a parallel plate capacitor, you have two parallel plates like that. You can place positive charges on the first plate and negative charges on the second plate. Now what it creates an electric field going from the first to the second, like that. So by storing charges on plates of a capacitor, we can also store energy inside that electric field. And this energy can be used when needed. So in this respect, a capacitor functions as a storage device. Now let's look at the concept of capacitance. Capacitance is a property of a capacitor. It measures how much charge can be stored in a capacitor. SI unit for capacitance is farad, or capital F. Now, typical values for capacitance of a capacitor will be in the range of microfarad or picofarad. So 1 microfarad is 10 to the power minus 6 farad, and 1 picofarad is 10 to the power minus 12 farad. Now let's look at the definition of a capacitance. Now let's assume that you have a parallel plate capacitor like that. We place positive charges on the first plate and negative charges on the second plate. The act of placing charges on these plates is known as charging a capacitor. Now we know the positively charged plate will be at a higher potential, let's call that potential V+, compared to the potential of the negatively charged plate. Let's call that V minus. So there is a potential difference between these two plates, and that potential difference is quite simply V plus minus V minus. Also note that these two plates contain the same amount of charge, but with just opposite sign. The capacitance C for this arrangement is given by the following ratio. Capacitance equals the charge divided by the potential difference. If the charge is expressed in coulombs, potential difference is expressed in the unit of volts, then we see 1 farad is equivalent to 1 coulomb per volt. Another important point that we can see from this equation is that by rewriting that equation as Q equals C times delta V, we see that the potential difference that is being built between the plates is simply proportional to the amount of charges that are present on the plates, and the constant of proportionality is the capacitance itself. So it fixes the amount of coulomb that can be placed on the plates of capacitor for a given potential difference between the plates. So the higher capacitance of the capacitor, more charges can be placed on the capacitor for a given potential difference. Let's look at the following example. A capacitor has capacitance of 6 microfarad. What is the charge Q on the plates with potential difference of 50 volts between the plates? So by using the formula Q equals C delta V, we can figure out the Q, the amount of charges that can be placed. C is 6 microfarad, so 6 times 10 to the power minus 6 farad, that is. Potential difference is 50 volts. And that's going to give you 3 times 10 to the power minus 4 coulomb. So this is the amount of charge that can be placed on this capacitor for this potential difference. Next, we shall see how geometry of a capacitor determines its capacitance. Now let's use parallel plate first as an example. So here you have 2 parallel plates separated by distance d, and these plates have surface area of a meter squared each. So now we place positive charges on the first plate, negative charges on the second plate, and that will create an electric field like that. Now we are to assume that the separation distance is much smaller than the dimensions of the plates. So let's begin with the fundamental equation. Capacitance equals the charge on the plate divided by the potential difference. The potential difference can be expressed in terms of electric field and the separation distance of the plates as follows. It is the electric field times the separation distance. We also know if you have very large charged plates, parallel plates, when we say very large parallel plates, that means the dimension of the plates are much larger than the separation distance between the plates. The electric field between a pair of such plates is given by the following expression. Charge density, or surface charge density sigma, over permittivity of vacuum, epsilon naught, because there is no material in the region between the plates, the same as in this capacitor. But the surface charge density sigma is quite simply the amount of charge divided by the area of that plate times epsilon naught to give you the complete electric field. Using this expression for electric field inside here and putting the expression for the potential difference inside that equation, we will obtain the following expression. For the capacitance, it's quite simply Q divided by delta V. So divide by delta V, that means dividing it by E times D. But we know that E is given by this complete equation, the expression Q over A times epsilon naught, over E means it's A epsilon naught over Q. So Q cancels, and the final expression for the capacitance of a parallel plate becomes epsilon naught A over D. So now you clearly see how a capacitance of a parallel plate capacitor depends on the dimensions of the parallel plate capacitor, namely the area of the parallel plates and also the separation distance of those plates. It also depends on the permittivity of vacuum, meaning what is in the region between the two plates. In this case, it's vacuum. So you see the capacitance increases if the area increases, if the separation distance decreases, and if we place some material in the region between them, namely a dielectric. A dielectric is an insulating material such as rubber or plastic or waxed paper, to name a few. When a dielectric is inserted between the plates of a capacitor, the capacitance increases. The reason is because its permittivity is higher than the permittivity of vacuum, namely that number. Permittivity of a material is given by the so-called dielectric constant of that material times the permittivity of vacuum. And dielectric constant of a material is usually greater than 1. We also note dielectric constant is dimensionless. It doesn't have any unit. So by substituting this expression inside here, we see the capacitance of a capacitor increases compared to the capacitance of a capacitor with vacuum in between the plates. Let's see how to calculate the capacitance of a spherical capacitor. So inner radius is Ri, the outer radius is Ro. So of course the electric field would go like that, in that direction, because this is positively charged, the outer sphere is negatively charged. The inner sphere has a potential V+, the outer sphere V-. So that's the potential difference between the two spheres. In exact term, it's KQ 1 over Ri minus 1 over Ro, which is quite simply KQ Ro minus Ri over Ri times Ro. Since capacitance is given by that ratio, rearranging this equation as to follow this ratio, we get the capacitance of a spherical capacitor to be that. Note, we have used the fact that K is 1 over 4 pi epsilon naught. Again, you can see the dependence of the capacitance on the geometric factors, namely the inner and outer radius of the spheres. Let's look at the following problem. The plates of a parallel plate capacitor, 4 mm apart, surface area is given like that. The space between them is empty, meaning you have vacuum inside. Potential difference of 8000 volts is applied. Find the capacitance of this capacitor. Note, this is a parallel plate capacitor with vacuum inside. So permittivity of vacuum is 8.8510 times 10 to the power minus 12. Area is 2 times 10 to the power minus 4. The distance between them is 4 mm, so convert that into meter, 4 times 10 to the power minus 3. And that's going to give you 4.43 times 10 to the power minus 13 farad. Part B, the charge on each plate. The charge is given by capacitance times the potential difference. We have found the capacitance 4.43 times 10 to the power minus 13. And the potential difference is 8000. And that's going to give you 3.54 times 10 to the power minus 9 coulomb. What is the capacitance if you fill up the material with dielectric constant 4.9 in the space between the plates? Note the capacitance now will become epsilon times A over D. This epsilon is the permittivity of vacuum times the dielectric constant. So substituting this in here, we get this, but note that this expression is just that value. So the new capacitance is K, which is 4.9 times the capacitance we computed in part A. And that's going to give you 2.17 times 10 to the power minus 12 farad. A higher number than that number as expected. Thank you for watching.